Hey there, Pythonistas. This is number 2 of a kind of a technical series. We're looking at somewhat simple challenges, but how do we tackle them in Python? It's easy to say something simple, but what really makes Python appealing to people? Why is it simple? Why do we claim that Python fits your brain? That's one of our slogans in the Python world. Python fits your brain. So what we have here is some cut and paste again from an email sent to me by another Synergetics research guy, and he's got this pattern going that he wants to be sure I understand. And we were doing some arithmetic in the previous video, making sense of one of those identities. I encourage you to go back one video before this. I'll put a link in the notes down below. Here I'm looking at creating a summation series, if you know what those are. If you've studied sigma notation or any of that, what sigma notation looks like. I think I have some examples here somewhere, like stuff kind of like with that big E stuff on them, right? The big Greek letter sigma. It's not really an E. Now I'm not going to use that because, like I was saying, it's expensive to get real math symbols or to get the typeset, to get the typography of 1800s math. You need to get an expensive package, or at least it's not free open source for me. Anyway, Python does what I need. What's important here is the Fibonacci number generator that we have. And if you know about generators, all right. If you don't, let me explain. Interestingly, we go straight into a while true loop right away, and we just keep going around in there forever. And if you're used to normal programming, you're like, well, doesn't that block? Meaning, don't we just spin in there forever and never relinquish control back to the caller? Like, would I dare call Fibo when it has an infinite loop in it? Doesn't that seem ill-advised? And the answer is, well, no, yield means what it says in terms of almost like a thread handing back control. This is what we call cooperative implementation. Instead of like preemptively people interrupt each other. Have you noticed a difference in a meeting? If everyone there is schooled to preempt, then you got to butt in with your comment. Otherwise, you'll never get your comment. It's all interrupt driven. And that's a model in computer science that is often used. But then there's also just yielding. And they say this in Congress too. I yield back my time. And when you're going around in a meeting, if somebody yields, then you don't have to interrupt them because they've yielded. So that's what's going on with Fibo here. The A gets yielded back, and then we do the update to get the next two sequence. We go ahead, and A becomes the new B, and B becomes A plus B, and we go around the circle again and again. You can think about that. So when I run this, which I'm going to do now, I get two output sequences because you can roll back the Fibonacci numbers to start somewhere a little bit earlier. You can go back to before 0 in the Fibonacci numbers. I don't know if you knew that. And I do that because I want to create this set of identities at the end of the day. This is the cut and paste, more or less, of what David Koski was sending me, that all of these phi expressions add up to 2. And I say phi expressions because we have phi to some exponent actually dropping in size. So you could think of a shrinking volume here, or something small, ever smaller. And they shrink at they start in different places, these two phi terms. So you can see in terms of the exponents, they're both going down just by 1 every time. But in the first case, we've started at 3, and we drop by 1 every time. By every time, I mean each row of this is another way to write the number 2, where we're raising phi to a third power and then another term, phi to the 0th power. So we have 2 terms here, and they both have coefficients. Now where I'm generating these coefficients from is interesting. I set two generators to be Fibo and Fibo 2 negative 1. The first time I don't have to give any arguments because I'm accepting the defaults, A equals 0, B equals 1. In the second case, I do want to rewind the Fibos to before Fibonacci numbers to before 0 and start there. And then I create this lengthy template here, which is going to be where I substitute in my next coefficient as I go on. So once you create a generator object, when you call this thing called Fibo, I'll go back to the generator now. When I actually call this thing, it doesn't start running an infinite loop. Rather, it hands me back an object called a generator object, which I can then trigger by feeding to the next function. So this is what we can do to anything that we call an iterator. Anything that's an iterator object, we can feed it to next, and it will hand back, yield back, give us back another results. And generators are definitely creating iterators. So I've got a list comprehension here where I'm just going to print out the two sequences of Fibonacci numbers, and we've seen those already. But then in the next sequence, I'm going to print out from this complex template where I'm substituting always my new versions, my new arguments for the two exponents and the two coefficients as we call them. So the coefficients again are Fibonacci numbers, and the exponents are just two dropping sequences starting from different places but just going down by one every time. And what's interesting here is first I build the expression and then I evaluate the expression. So on the left side, I've got all the way up to and including the arrow that's pointing to the right. That's just printed out like using typography. That's just a string. It's not doing any kind of math. It's just printing out a well-formatted string. And then I just take the meat. I just take not the 2, but the expression after the double equal. I just take that. So that's what XPR is, EXPR. That's just the meat and potatoes of this thing. I execute the actual expression in floating point. So it's not super precise compared to like some other types I could use, extended precision. So you see the result coming out is not always 2 on the nose. There's a little bit of floating point noise. But we could figure that as what it is, floating point noise, and also prove why is this true using algebra. Why is this identity always correct? I'm not going to do that here. I'm just going to turn you back to whatever you were doing a minute ago. Enjoy.